Was later a professor at Carnegie Mellon before he moved to Zurich and has now been at ETH for quite some time. So Thomas's work spans an enormous scope. So he works on things like systems, in particular networked systems, visible light networks, things like that. And then it goes up the entire stack. We are compilers, we are programming languages, programming models, all the way up to testing. And so today he will talk to us about dynamic checking and applications to security properties.
Hey, is this audible? Okay, good morning, everyone. So what I will try to communicate to you is the idea that we should use more cycles, should waste more cycles on checking. So in case you think it's a nice day and you want to spend the next 40 minutes outside, here is the summary, so you know what I talk about and you can still tell your management that you attended this talk. So, you know, we all appreciate that actually there is something cut off in the beamer. Well, we'll do the low resolution version. I hope the content is not affected by that, but so let's see. So no, okay. So the right-hand corner is being cut again. So so there exists a range of languages that shield programs from all kinds of attacks. And these are kind of useful because they kind of allow you to make certain assumptions about the program, but they're like a walled city. I mean, they kind of tie you in and you can't get in, but you can't get out. And as a result, yeah, these languages are useful in many scenarios, but not all. Now, there are also many programs that are written in unsafe languages, and I'll get to that in a few seconds. And these languages are apparently useful. Like the gates in a wall, because they allow you to reach out to the system, reach out to the lower underlying hardware, or reach out to other parts of the system. So they're even so useful that you may not even know that you're using one. Now, it would be nice if our tools could deal with all the complexities of these unsafe languages, but they can't. And until we have reached the time that we can actually deal with all the problems, my point is that we should use more cycles to check what is going on and to check our system so that we don't become victim to all kinds of attacks. And I will look at a specific technique, dynamic contraflow integrity, that is a promising technique to actually detect attacks that are based on a wide class of approaches that all in the end rely on corrupting memory. So, your memory-safe languages, I would say, they all have nice properties. They have automatic memory management. They all hide address arithmetic from the user, so we don't get any buffer overflows. We get no out-of-bounds array accesses, etc. And all these other nasty problems don't exist. And of course, one necessary condition for this is that we don't allow arbitrary type conversions. If a type conversion happens, it must be either checked or it must be obvious that this is legal. So as a result, these languages restrict the address space or the part of the memory space that a program can get to. And there are various ways how you can do this, either because you design the language that way or because you use static code analysis to prove that certain properties hold. And so in the end, this set of languages gives us the hope that they are a weapon against memory errors. And I use that term memory error to refer to any kind of corruption of memory. Well, unfortunately, these memory errors come in all kinds of forms, and as a result, they have been exploited in various settings, or they can be exploited in various settings. Because if some attacker is able to corrupt the system's memory, then the attacker is able to do something that the original owner or the original person who wants to run the program did not intend. If you have a way to modify a processor's memory in a more or less controllable way, then whoever has this capability can get the system to do whatever it wants. And in the worst case, if the system can modify any arbitrary location, with any arbitrary value, then an attacker can gain the right to execute arbitrary code, and then everything's possible. So these kind of memory errors exist, as we all know that, in unsafe languages, and it's a very old problem, right? All these languages that do not enforce memory safety actually are exposed to this problem, and that's kind of annoying. So as I said, we have these safe languages, so couldn't we just use a memory safe language, and the problem would go away, and we would have made it impossible for these kind of people to earn a pretty comfortable living. Well, unfortunately, the situation is unfortunately a little bit less enjoyable. So these safe languages, at least the popular ones today, they all run on some virtual machine. Now, since that term virtual machine is overused in computer science, we say they run on a language virtual machine. And the most known example that you probably also have been exposed to is the JVM, the Java Virtual Machine. And this kind of virtual machine provides a framework for access control. It provides an environment for scheduling, for multi-tier compilation. That is an important aspect because you want to get performance at some point in time. So that basically is the environment that these systems work on. And that's great, right? So except that this language VM doesn't come out of thin air. It has to be implemented. And at some point in time, this language, at some layer, I should say, this language VM may be implemented in an unsafe language. Yes, there are some efforts to even implement these VMs in a safe language, but, well, there is still, the user interface to unsafe libraries. There is the option to do native calls. And so these doors or these gates exist, and someone can use those to do bad things to you. So memory errors are still an issue, and not just an academic one, right? So it's a nice example done by a group that used this idea. They used the memory error in the type font handling to attack a JVM. If you want to look this up, I have here the reference, right? That was an attack that targeted Java, in Oracle's Java version, which is the industry's a very popular industry. And what these attackers did, they managed to get were able to execute the code they wanted, and they were able to completely bypass all of the state-of-the-art defenses. I'll say a few words about defenses later on, because there exists, of course, a wide range of defense options, but they were nevertheless able to do this and demonstrated this at some meetings. So the point is that you may be thinking that the world's safe if you run in Java. It isn't, right? Now, of course, it's not just unsafe because you have to deal with Java implementation that's built on an unsafe language. I would predict that unsafe languages are going to be here for a long, long time. I mean, C and C++ happen to be, for better or worse, very popular. I mean, just someone just showed us a piece of, was that C code, right, Patrick? Yeah, I think so, right? So it's a very popular language. And yes, there are alternatives, but those don't work always. And there is a growing list of alternatives, and these work in certain situations. But nevertheless, for a variety of reasons, these unsafe languages are going to be with us, and they are still very popular. It's only this year, there is some company that does a survey, tries to see which language is the most popular. And this is the first year, so there is hope, that Java made it onto of the real programming languages, not things like HTTP or PHP. So this is the first year that Java made it in position 1 and replaced their C, which happens still to be on position 2. So I think this is a real problem, and we ought to take a look and see what we can do about it. Now, unfortunately, the problem is old, right? So many, this problem has been known almost since the day that C became popular, and we all know that these memory errors can lead to serious problems and serious situations that you don't want to be exposed to. So, there exists this repository of common vulnerabilities and exposures called CV. They give them numbers, you don't see the E at the end, CVE. And they classify attacks that come into those that are of a high severity, medium severity, and low severity. And you see they have these three different kinds of attacks, those based on memory errors, those based on cross-scripting or cross-site forgery, and those based on SQL injection. And so you see that these low severity errors there, those scripting, cross-scripting or cross-site attack approaches actually overwhelmingly presented. But if you look at the high severity errors, you see that memory errors almost make up a little bit more than a third, almost 40%. So that's clearly nasty, because those are the errors that in the end allow you to do really nasty things on your system. So if you look at the software system as it exists, right, there are all these many components, right? So we have here, hardware, we have an operating system, we have libraries, and then we have maybe a Java, JVM, a web browser, some other application. And if you look at those, well, where could there be, where is there an opening for someone to attack? Well, it's really almost everywhere, right? The only thing that you can't easily attack is the hardware, in part because there's no longer writable control store on these devices. Otherwise, I'm sure someone would find a way to attack there as well. So everywhere, you can attack. Now, if you look at the world with Java, it looks a little bit different, right? So we have here, the Java virtual machine. But as I showed you earlier, right, even in those, since the Java virtual machine at some point in time is built on some lower level system, you have also enough opportunities to attack such an environment as well. So we do have to fight with the fact that these problems exist. And if you summarize it, right, the unsafe languages, they allow low-level access to memory. They only enforce, have a very weak notion of typing. And because they have explicit memory management, there are enough opportunities for a programmer to get into trouble. So if you look at these memory errors, I'm sure you have been exposed to those, right? You can either do a spatial reuse or temporal reuse. You either you get a pointer to a region that is not valid at this point in time, and then you overwrite this, or you use a pointer to a memory block that was valid some time ago but isn't valid right now, and then you use this pointer to modify your program. And once you have found a way to modify some part of the of your data space, right, then you can actually either corrupt information that leads the system to think that some region is only affected by it, or and that's what really is the annoying part about this, you construct more complicated primitives. So just writing one location isn't really what you're interested in. A bad attacker wants to be able to, in the end, redirect the execution stream to a place that the attacker can control. So basically, as long as if you want to make sure that some attacker is not successful, you have to make sure that you don't allow the attacker to have the access to a write primitive that allows the attack to write any value to an arbitrary location. So you can use all kinds of bugs to get there. But if you look at the kind of attacks that persons have used, right, there is a paper that one of my colleagues co-authored that kind of classifies these attacks into 4 groups, right? So there are the code corruption attacks, there are those control flow hijack attacks, there are data-only attacks where you modify some part of the data space, and then there are information leaks. Now, all of those have some drawbacks. I want to focus here primarily on that second category, the control flow hijack attacks. Why? Well, if I'm able to hijack the control flow, if I'm able to get a program to execute what I want to do, then I have reached my goal of being able to execute arbitrary programs on a given system. So this is really the most, it's a very powerful attack. And so what you want to do from an attacker's point of view, right? You want to hijack the control flow, and you want to be able to redirect the execution to some attacker-supplied arbitrary machine code. So that's one option. Or if you can't insert any code, and that is the nastier part, you may be able to reuse existing code. We'll get to that in a second. You'll be able to reuse existing code to do what you as the attacker wants to do. If you get the program to execute the code in the right sequence, then you are able to get the system to do what you want to do. And the key idea is that you somehow have to corrupt the code pointers. You have to somehow modify those places in memory that tell the processor where to continue execution. So you have to either modify return addresses, function pointers, vtable entries, exception handlers, jump buffers. Modern language, there are enough options for you to do something if you want to change the control flow. And as long as someone is able to corrupt one of those, bad things will happen. So now how does this is probably known to all of you, right? How do you go about changing the control flow? Because you have to understand this part if you want to understand how someone wants to hijack the control flow. Well, almost all the computer architectures, the instruction sets, support some form of indirect branch instruction. So on the x86, right, there's a return instruction, there is a jump, which happens to be indirect, there is a call instruction that's indirect. All of those go through some location in memory, right? So here I have some location in memory that contains an address, and this address refers to some desirable function out there. And so if I do a branch through that address, I basically jump to this location out there and continue my execution out there. And an attack basically works by corrupting this place. If I have a way to change this location out here, then the program will still do a branch, a branch through that address, but instead of transferring control to the place I wanted it, it's going to transfer control to the place that's indicated by this location out there, and that would be some evil code. And once I have done this, I would be able to do whatever I wanted. Now, of course, in a real system, right? How do you find a way to do this? Well, there could be a pointer on the heap, right? That in the ideal world refers to this function out here. Out there, you're going to do such an indirect branch or indirect jump here in the form of an indirect call, and then you look at this location out there, and you continue computing where you hope to continue. Well, here, the programmer has been able to change this, the attacker has been able to change that location, and so if the program executes this call, rather than transferring control to this place down there, it transfers control to this area that you don't see out there, and that is out there, right? So now, of course, this approach has been well known, so what can we do about it, right? So, well, there are a number of defenses that are commonly employed. So the first one, of course, is don't make data executable, right? So the idea here, somehow my attacker was able to put something either on the stack or in the heap, and that is data from the program's point of view, right? So if I prevent the execution of data, then I will not be able to pursue this kind of attack. And so various machines have a bit to indicate that this region or section of memory is not executable. Or you can get the operating system to help you and implement something that's called like data execution prevention that prevents the execution of certain parts of the address space, so you can't put data, you can't turn these data into instructions. And that's kind of great, right? So because that makes it no longer possible to take this route, right? You can't put attacker code into the heap, or you can't put attacker code into the stack, and therefore, because these data regions are no longer executable, and that's great. Now, unfortunately, there are some realities of life that limit the effectiveness of this attack. So, all of you probably have heard the term just-in-time compiler. You would like to use one of those to get better performance. Well, a just-in-time compiler, unfortunately, produces data that at some point in time become code. right? So therefore, the JIT won't work if no data can ever be executable. So we need a way to, at some point in time, change something from data to code. And so that's kind of a sad fact of life. Now we can say, well, we don't allow self-modifying code. Well, that's a good idea, except at some point in time, if you have just-in-time generated code, then you must find a way to actually turn data into code so that your JIT compiler can produce the kind of program that you want. So now, but given that we have found a way to control this, or maybe what else have we reached the state that we can be happy and lean back and say, well, great, now our system is safe. Unfortunately, as I alluded to earlier, well, it may not even be necessary for the attacker to insert code. It may just use the code that's already available. A large program with many libraries contains lots of code. And so there has been a growing interest in a group of attacks that are called code reuse attacks. There are attacks that you can almost attack frameworks that you can download from the web. There is one approach that I will look at more, which is called return-oriented programming, where you use a specific approach to find the code snippets that you would like to use to get your work done. There exist variations. Rather than using the return instructions, you're using jump or call instructions. Once you understand the risk or the problems that are caused by return-oriented programming, the other ones are pretty obvious. So now, of course, it's difficult to use these code snippets that you find in your code to do any arbitrary thing you want. But you don't need that, right? All you really need to do is you need to find enough instructions that somehow manipulate the protection flags. If I can find code that will reuse will modify the protection flags, which then I can turn those off, and then I can go back to my original model in that I use the stack or the heap to contain the data that I want to use, can use the data region to contain the attack code that I want to get executed. Now, will I find such code somewhere in my system? Well, I mentioned already, because you want to support a JIT somewhere, there must be somewhere a piece of code that will manipulate the protection flags, right? So if I can find this code, and if I can get this code to do what I, as the attacker, want, then I have won, right? So if you are able to identify this place and then do something with it, then you can attack the system. And that's basically the idea of return-oriented programming. What you do is you kind of look for code snippets. Oh, here I have somewhere something that pops EDX followed by a return instruction. And here I have two instructions that pop two other registers. And here I have an instruction that moves something from this register in the location referred to by this register. And here I have something that moves the value into a register. So if I have these pieces somewhere in my program, I can manipulate manipulate the stack to put in there the addresses of such pieces, then the program will kind of follow the sequence of return instructions, and by doing this, following this, unwinding the stack, will do the kind of steps here that I wanted to do, that will manipulate the system to be in the state that I want to be there. So this is a very powerful way how you can attack a program, and that is really from that point of view, very successful, right? You can do almost everything that way. And as I mentioned earlier, you can do this not just with return instructions, but you can also do this with jump instructions. These little snippets that you have here, right? They're called gadgets, right? These little pieces out there. So what a dedicated attacker will do, he or she will look for appropriate gadgets that can be put together to do something bad. Now, of course, for this to work, an attacker needs to know where things are in memory, right? You need to know where the instructions are, and you need to know where the data are going. You need to know where a data region is that you might want to manipulate. But so you need the address of these gadgets. You need sometimes the address of the injected code. You might need the addresses of data pointers that you need the addresses of the data pointers that you want to corrupt, right? So you need to know where things are. And sometimes it's even enough if the attacker just knows roughly where things are. Why? Because sometimes corrupting, the low order bits are enough. So if the attacker needs to know where things are, why don't we just hide that, right? And that's the idea of address space layout randomization. So that all model that you just put, a sequence of bytes into memory, this is long gone. Modern systems implement this idea ASLR and randomize your either your code pieces, right? They put the libraries into different locations. So each time it depends now on the system. Some systems pick that random value when the system is built. Others pick it when it's booted. So there's a range of quite a number of options you can use, and that exists. So the key idea is that you try to protect base addresses or code blocks so that an attacker can't be sure that on a given system the data is in this location or the instruction is in this location. But of course, nothing is perfect, right? So there are ways to get around address space layout randomization, right? So first of all, a dedicated attacker somewhere in a place where it's cold and not much else can be done, right, could just try all possible addresses. Well, that's kind of, these brute force attacks are usually not that successful. But unfortunately, it's also often possible to exploit memory leaks. So you can, if you know a system well enough, you can figure out that if you know some address, and you can find a way to get to this, then you know that this address gives you a base, and then you can figure out some offset, and with this you can figure out where a certain part of memory, a certain value, a certain variable or field that you actually want to protect actually happens to be located. So you can construct or enforce a leak by memory corruption, or you can even enforce these leaks in other ways. And here's the key idea is that here is maybe an address that for some reason leaks out. So once I have this address, right, and I know the static offset of the from here to there, which I can often find out. I can just do arithmetic, and then I find the exact location of the value of the memory variable that in the libc, for example, ought to be protected. So basically, these execution protection and address space layout randomizations are great defenses. They kind of work fine. They make it definitely harder for someone to attack a system. And if they're used correctly and all the time, they can be quite effective, but unfortunately, it's not enough. So what other ideas have been exploited? Well, you've all heard about using a compiler, right? Compilers are useful, right? And so you can get the compiler actually to help you by adding extra data fields, for example. Very popular, you have canaries or cookies that modify the data layout so that as a result, the attacker doesn't know how the system looks like in a given location. Now, unfortunately, all of those require the source code. So this it works on some systems when you have access to the complete source code, but it doesn't work in many other settings. I don't know if you know how these canaries work, I assume, right? So you basically go and add a buffer, right? Add a field to the buffer so that if someone overwrites, then they will also destroy the canary. But yeah, that all works because it relies on a secret. If you need to keep the canary value secret, because if the canary value is known, then my attacker will just overwrite my canary with the expected value. So and we all know from computer science that secrets are not a good way, right? So, so we need something. I mean, this is certainly useful and good, but we need something else. So, because as I want to kind of point out, right, a determined attacker can find enough ways to get around these defenses to still use code reuse techniques and modify memory. So if you take a step back, right, and you see, oh, they have all these defenses, where you realize is these attacks, that these attacks are definitely delayed by such defenses, not being able to execute data memory as instruction, or randomizing the addresses and making it harder to guess what you want to modify, make it certainly harder on an attacker. And they make it harder for the attacker to access memory. But programs actually execute instructions, and execution of instruction is more than just reading a value in memory. So if you want to have better defense, we ought to work towards protecting the execution of the program, to protect the execution of the program. And if I look at a dedicated attacker, right, that can arbitrarily corrupt data and pointers, and that can read the entire address space of a process, right, with maybe the exception that because data execution protection is turned on, etc., they can't execute instructions from regions that are protected by the NX bit or by DEP. If I have this as the only restriction, I have to think, how can I make sure that such an attacker, does not gain a way to control program execution. And so the idea that came from some researchers at Microsoft was that an attacker that wants to do something bad would have to change the control flow of the program. So our runtime system in VM must make sure that the control flow stays on the intended path that has been envisioned by the original author of the program. And that's the idea of control flow integrity. So control flow integrity tries to build a control flow graph, and this one should be as strict as possible, because otherwise it's not going to be very useful. And then you ensure that control flow stays within this control flow graph as defined by the system that has built this graph. So the idea was originally published in 2005 by this group of researchers at Microsoft. That was at a conference, and later there is a journal paper. And that was a very, very clever idea that actually we could check that the control flow stays within the realm described by the control flow graph. And over the last, I guess now 10 years, right, various CFI implementations have been proposed, and all of those were based on either a compiler, because then the compiler would give you enough or more information, or they used binary-only approaches, meaning they took the binaries and then rewrote those to make sure that they detect control flow changes that deviate from the path that we want to deal with. That was envisioned by the programmer. So as I said, you want to have a control flow graph that is as strict as possible. And if you manage to do this, and then no path within the control flow graph can be misused by an attacker, then this control flow integrity policy is secure, because then you can only walk through the program in along those paths that don't allow an attacker to modify any part of memory. So if you look at the control flow graph, right, the control flow graph basically tells you, here are basic blocks, right? Here is a control transfer from here to there, another one from there to there, and here we have a return or some indirect jump, or if I go from here, I have an indirect jump. I basically figure out which control transfers are possible in my program, right? There may be direct branches, there may be indirect branches to transfer control. And if now an attacker comes along that modifies this return instruction, instead of going back to this basic block out here to transfer control to some bad block, right? This would work if we didn't check the control flow, but in the present, or from here, where you transfer control to, from this place out there, in the presence of control flow integrity protection, you know which transfers are possible. So from this basic block, you can only go to this basic block, or from this basic block, you can go to these, or to this basic block, but to no other basic block. And if now an attacker comes along and transfers control either from this point here or from that point there to the red basic block, then the control flow integrity system would discover this and would complain and stop it, right? So now this is kind of a nice idea, but the approaches that were proposed in the past were just had a number of drawbacks. So either they were, they had a control flow graph that was too permissive. Obviously, if you allow everything to go everywhere, then you don't have much protection. So you need to be sure that your control flow graph does not over-approximate too much. And furthermore, or at the same time, you needed to recompile the program. You need to have access to the source code so that you can actually provide this protection. And then, which is a real killer in many practical scenarios, these approaches don't support shared libraries. Now, I don't want to go through shared libraries in detail, but as a result, there is not just research going on how to harden a system, there's also research going on how to harden an exploit. So various groups have been able to take existing exploits and get these to work on systems that were that had implemented control flow integrity. And the main point is that all these approaches that are static just don't give you enough protections. You either over-approximate or you don't do what is necessary to detect attackers. So you need a dynamic approach. You need dynamic approach that discovers, as you execute the program, how your control flow graph really looks like. And so we implemented such a system that we call lockdown. And this enforces a strict control flow integrity policy for binary, but supports shared libraries and dynamic loading, which are two important properties of popular operating systems. And so we construct and enforce that control flow graph at runtime. And of course, that costs some cycles. So the way we do that is we take the program and that is to be executed and let it be handled by a binary translator. And so we never execute programs right out of the box. And this binary translator, of course, employs a large number of tricks to make sure execution is still reasonably efficient. So we have a large code cache that contains stuff that has been translated and passed through the translator. And then we basically run this program, and we have, as part of the system, this control flow transfer verifier that checks that if the control transfers done by the program actually follow the rules that we have out there. Now, for this to work, we need to make sure that this system doesn't get polluted, right? So we need our own loader. Otherwise, you could use your loader as your entry to get into the system. So we had to implement our own loader. But once you do that, then you are able to have a system that gives you a much higher degree of protection than other systems had before. So the point is you have the binary translator that instruments the code with additional checks. And so this is a user space virtual machine, if you wish. And this one ensures that no untranslated code is ever executed. So the, this gives us a better protection because we are now able to separate the various parts of the system. And we would even be able to get even higher guarantees if we, for example, would be more consistent in protecting some area as read-only during execution from program out of the code cache. So now, I think I have had 45 minutes, Peter, right? I have 5 more. So, right. So I don't want to go through the. So basically, the key idea is that you have various policies that tell you what kind of control transfers are possible for calls, jumps, or returns, right? So, so if you, for example, have here a system where you import various symbols from either libc or some other library, right? So now here you see this one, this libc, exports various fields or various addresses. Now, since this piece of code only transfers only imports the yellow, the names shown in yellow, namely put string, but not mprotect, the control transfer from this part to mprotect would be prohibited. Also, this is a legal entry point by the rules of the libc. So by making sure that a piece of program only goes to the part that it actually is allowed to go to, you are able to restrict the transfers dramatically. And the same applies for jumps, right? And for returns, well, we have to do something there too. If we allow someone to push the return address on the stack, then someone could modify it. So we keep in a protected area a shadow stack where we keep the return addresses that we need. So if a program does a call, we put the return address on our shadow stack, and if the return happens, we check if the two are still identical, and if not, then we are able, and we raise an exception and alert the user. So there are a bunch of issues that still deserve further attention in that field, right? So how do you actually detect all the idioms that are used in real programs to affect a control transfer? How do you do that in the presence of stripped binaries which don't contain all the symbol information that you might like to do? Because real life programs contain sometimes control transfers that don't adhere to the rules that are just simple and as they are that I presented earlier. So, and of course we would like to get the overhead of any checks down into an acceptable range. So we did a preliminary performance evaluation, and there are good and bad news, right? So that's, So the bad news are there are some programs where you really pay a high price, 150% overhead, right? The good news are there are programs for which you pay a 1 or 2% overhead. Well, if you do an average, and we all know how to manipulate averages, it's about 20%. Now, 20% is not free, but it's certainly a lot cheaper than some of the problems that you're dealing with. In our set, only 5 benchmarks it cost us more than 45% overhead. Now, of course, the checking of the control transfers isn't that expensive. The binary translation alone has an overhead of about 15%. So if you wish 15% for the binary translator, which gives you a variety of benefits, plus 5% overhead for the control transfers. So that's not so bad. I'll go over the various approaches that we can use to evaluate the effectiveness. There are various metrics, and they will tell you that this approach only allows 1% of the targets of locations as a target for an attacker. Now, 99% protection sounds really good, right? Until you look at the numbers, right? LibreOffice has 56 megabytes of executable memory. If you have 1% left as a attacker, as a target for an attacker, that still gives an attacker almost a little bit more than 500,000 potential targets. So 1% is really bad. So because an attacker usually just needs a handful of gadgets to mount a successful attack. So among these 500,000 potential targets, you're going to find one that moves code into the register that you want to modify. And you'll find another one that puts the value you're looking for into this register somewhere else in the program, right? And you kind of glue them together and you are in business. So, so we definitely need a better way to evaluate these approaches. I'll kind of go over this in the interest of time, and you can always ask me later. But there is still, I think, a lot of work that needs to be done to evaluate these various approaches and have good metrics that tell you what actually works and which attacks don't work. So the key idea, right, of a dynamic control for integrity system is that we use a binary translator to rewrite programs on the fly. And that is a practical solution because it allows you to work on any arbitrary binary that you are dealing with. And that's incredibly important if you want to have a solution that really works in practice. Now, admittedly, binary translators add overhead, but you know, there is no free lunch, right? And then the binary translator together with a dynamic control flow integrity guard system, you know, it protects you against some attacks. It doesn't give you complete protection, but it gives you a protection against a much wider range. And the key point is, right, make sure you don't execute native code. Make sure there is one level of indirection in your system that protects you from actually protects you from executing code that an attacker has manipulated. So this work was done with, together with several of my colleagues, right? 2 of them were former master students who now actually are trying to started a company that sells this idea as a way to check attacks that come in through PDF files. And Matthias Peyer is a former PhD student of mine who now works in the Midwest in the US. And so as a concluding remark, right, control flow integrity is a great idea. It allows you to protect execution paths, which I think is what you want to do. Don't want just to protect memory, you want to protect the execution of a program. But static approaches are not enough. You need a dynamic approach, dynamic checking, dynamic building of the control flow graph if you want to be effective. Of course, this is not yet final in the sense that there is no more work that needs to be done. There are many options to do something. You can look at more efficient implementations. You can look at finer, more accurate control flow graphs. But the bottom line is all of these approaches rely on your willingness to spend some cycles on checking. If you just want to run your program on the bare machine, this will never work. So my view is actually that no user program should run on bare hardware. Given the number of cycles that we have available, it seems like really a stupid idea not to waste some of them for checking in situations where there is user code or user interaction. And yes, a layer of indirection adds overhead, but that's actually what gives you the chance to protect your system. So thank you for your attention. I'll be happy to take any questions.
Yeah, thanks for the talk. So I had a question about this exactly what the property is. So this is a property on paths, right? It's like a sequence, and so yeah, that's fine. But what it means is that I mean, it could be an arbitrary property on a sequence. It could be that you can have A, B, C, D, F, G. You go for a while and then say, oh, some event happened. Now I have to look over the entire path maybe multiple times. So this, I mean, this could be very expensive. Right, but what you're checking here is somehow pairwise, like the last event with the new event. It's only on the right. Mm-hmm.
I think what is a value judgment, right? I think a 20% overhead I could tolerate. A 20x slowdown, I could probably not tolerate, right? So, you know, if it's 20, maybe 50% would be okay too. Now, 10% would be better as an overhead, right? I think that would be one of the interesting questions to investigate. You know, how could we add history, maybe a little bit of history, without going through, you know, without throwing away performance?
How do you make sure that the attacker intention is not to prevent your program, to stop your program, because in that case your protection make the attacker job easier.
Yeah. So okay, so there is no complete protection, right? So now this kind of if you're thinking about like denial of service attacks, right? There are other ways to deal with them. You know, that basically would not be covered by this kind of you know, by this kind of defense, except that if I can make sure that the attacker isn't able to place somewhere a halt instruction, right, then I have actually ensured you know, some level of security, right? Basically, I want to make sure the attacker never deviates from the path through the program that's allowed, and that means the attacker cannot execute an instruction that would either put an arbitrary value into a register or will put an arbitrary instruction into the code segment. So, you know, in some sense, I don't care if the attacker wants to just, you know, blink the screen or halt the system. As long as I make sure the attacker doesn't have a chance to do whatever it wants to do, that's fine. Now, of course, you could still have a denial of service attack where you kind of, you know, throw so much at a system that the system is useless, but there are different defenses that exist against this kind of attack.
Maybe a shadow stack you cannot correct.
Well, correct, I mean, I would not dare to correct because you see something is wrong. You don't know, you see, you know that the attacker has modified the return address. You don't know what else the attacker might have modified. So just putting the old return address in may, you know, just be a nice way to get your attacker in business, because then they just have to, then they have to add one level of indirection. Yeah, so that would be.
Okay, let's take one more question before the break.
So in the control flow integrity approach, as proposed by Microsoft Research, the compiler builds in the information about each particular pass and also. So now you don't have that information at runtime.
Right.
So are you relying on just the what's the export?
Well, the export table, and you look at for certain idioms, right? So obviously, you know, there is let's say there's a call site where someone goes to the V table, right? Obviously, entries in the V table, because you know that it's a V table and not some arbitrary location, are allowed, and you make sure that the V table is protected as well. So basically,
so you can, actually, more generally, you can effectively, for certain binaries, you can put as much information as you want by instrumenting them as you do actually.
Yes, except that not all binaries will come with all the information that you would like to start at, right? So but then you have to discover as you go on,
so
right?
You discover, or you can also add as a policy, can you?
Yeah, well, yeah. So
I mean, if this is something GNU library that's available downloaded by everyone, you could have this information built in.
Yeah.
Okay, so let's take the rest of the discussion offline. Thank you, Thomas.